Yeah, shall we get started? 我们现在开始吗？Okay. So yeah, to be honest, I have prepared something that to share with you. It's a little bit too technical. The title is from. Is it small? Big enough for you? From Sumcheck to SNARKs. So first of all, just a quick story. So how many of you have heard of Ziggy SNARKs or SNARK for sure? Please use your hand. Only half? Okay. Yeah, now how many of you have heard of Sumcheck protocol? Please use your hand. Sumcheck protocol? No? Okay. Yeah, so another, sorry?
Is it related to checksum or is it like different kind of protocol?
Different. It's it's coincidence at Sumcheck. It has nothing to do with Sumcheck. Okay. So another survey is like, how many of you know that so the meaning of zero knowledge, because zero knowledge proof is kind of a buzzword, and a lot of projects they claim they use zero knowledge proofs to prove something like a privacy or scalability something. So what is zero knowledge? Why it is called zero knowledge? How many of you can give me a very short explanation or description about what zero knowledge is? Anyone?
It's like basically like proving something without actually exchanging the whole information.
Yeah. Okay.
It's like proving something without letting the person know that this is something.
Yeah.
Okay. Good. Very good.
It's like proving something without revealing the actual data of the other side.
Oh yes. Very good answer. So zero knowledge proof. So yeah, I think the first topic today is like, let's talk about some very basic concepts for ZKP for sure, kind of zero knowledge proofs versus Ziggy SNARK. Ziggy SNARK. So what differences between these two different concepts? Anyone can answer? So what differences between ZKP and Ziggy SNARKs?
It's not really technology or the way you write zero knowledge proof.
Yeah, very good. So Ziggy SNARK is kind of one of a family of protocols which implementing zero knowledge proofs. Zero knowledge proofs is kind of a bigger, much bigger concept, which so yeah. Here let's say put it here, zero knowledge proof. So first of all, zero knowledge proof is a proof. Because it's not a kind of proof that we learned, for example, in middle school, high school, that the teacher asked us to write some formal proofs for some mathematical theorem. So it's not that kind of proof. So actually, zero knowledge proof is a much more broader or is extension or generalization of the traditional mathematical proofs. So zero knowledge proof is a probabilistic proof. Probabilistic proofs. And also the interactive proof. Active proof. So it's not a proof written on paper. It's a proof in form of interaction. So imagine that, in an examination, for example, a final examination. So when I get a paper being asked to write the form proof for some question, that I leave it blank, and I hand on submit the paper, and then later on the teacher asked me, okay, so you leave it blank, so I have to ask you, I have to challenge you if you know the answer. So then I will have a conversation with the teacher, so to convince teacher that, okay, actually I know the proof, but I don't want to write it down. Okay, so it's an interactive proof. It's not a proof written on paper, from proof all the way to the QED, right? It's a symbol like indicating that, okay, actually you're convinced all the verifiers. So it's an interactive between two parties, prover and a verifier. So zero-knowledge proof actually is a protocol between one prover and potentially multiple verifiers. So okay. I have to say there's many different zero-knowledge proofs. For example, some protocols will allow the verifier can be public. That means anyone can check if the proof proposed by prover is true or not. Or some proof can be very private. So only some specific verifier can check the validation of the proofs. So, but here in the crypto world, so almost all, 99% of the proofs are public verifiable. It means that, okay, the zero-knowledge proof can be verified by anyone. So it's the same philosophy with blockchain, right? So anyone can show the proof, put it on chain, and even after 100 years, so probably in the future, some aliens can also verify if the proof is valid or not. So first of all, zero-knowledge proof is different from a traditional mathematical proof. First of all, it's a probabilistic proof. That means so there still be very small, negligible probability that the prover can cheat, but just because the probability can be very small, even impossible. Because, for example, if here's 2 to 128, 1 over 2 to 128, the probability that this number is very small. So even it's a probabilistic proof that, but we can ensure that, okay, the prover has no space to cheat. So it's not 100% proof. It's not like the formal mathematical proof. That proof can be 100% perfect proof. But here it's probabilistic proof. So it's the cost we can extend or generalize the proof to a much more broader concepts. So the traditional mathematical proof is it's a non-interactive proof or one round proof. Okay. Okay. First, secondly, it's an interactive proof. They need the prover and the verifier they have to, the verifier should ask many questions to prover, and prover have to reply honestly with the answer to convince the verifier. So, but in Zk SNARK, it means that the N, there's the N right here. So N stands for non-interactive. So the question here is that zero-knowledge proofs naturally needs interaction between prover and verifier, even a couple of rounds, maybe 20 or 100 rounds to convince the verifier. But why the SNARK can still make a non-interactive proof? So anyone know the answer? Or or have some intuition that how we can achieve that. So now we want to convert that interaction or to eliminate the interaction entirely to make sure that, okay, the proof can be non-interactive. So that's, okay, the interactive interaction is not good, for cryptocurrency because we cannot ensure all the time the prover can be online, right? The prover just submit the prover, then disappear. So if every prover have to online to waiting for some verifier to check, to challenge, that will be too inefficient, right? So it's not suited for the cryptocurrency applications. Now we need the SNARK. So N, here's the N, that means, okay, it should be non-interactive, but how can we do that? So anyone know the answer or have no idea?
It's like trying to compress everything in a single call, something like that.
Because every round, the verifier have to challenge something.
Yeah.
So the point is that to make sure that there's no space for prover to cheat. So the prover cannot know the challenge or the question in advance. Otherwise, the prover can, we'll cheat something, we'll do something badly, so to break the protocol. Yeah. Okay. Here we have to use the cryptography to convert this protocol into a one-round protocol. So we have to do that, conversion or transformation here by using some cryptography tool. Okay, the basic idea here is that. So there was some results, probably 30 years ago. So some Zigzag proofs. So we put some restriction on verifier, saying, so okay, all the question asked by verifier should be a random number. So the verifier can only ask a random number. Another general question, for example, okay, is it today rainy, or have you had dinner? So it's not like that, general question. So the verifier can only ask question like, show some random number, and the prover, and according to the random number, do something, reply to convince verifier. So that protocol is called public coin protocol. What do you mean by public coin? First of all, it's like a toss a coin. We get a head or tail. For example, if I toss a coin for 100 times, we will have a 100 bit long random number, right? And public, that means that the verifier should toss the coin in the public. Everyone can make sure that the coin is in the fair way to generate a random number instead of some random number which maybe not so random. Okay, so for this kind of protocols, public coin protocols, now we can use the hash function to simulate a verifier to generate that random number. So the hash function can hash something, the transcript, generated by the interaction, the hash the interaction and generate the next round random number. So to replace of the question asked by a real verifier. So that's the way that we can convert a multiple round interactive proof into a one round non-interactive proof. So that such that we can use that non-interactive proof in cryptocurrency applications. So I will stop here for 2 minutes. So, okay, it's time for a question. So ZK SNARK, I will explain other, meaning of the rest of the letters. What A, R, K, and Z, K, what that mean? So here, any question? So or something not so clear, so I can say it again. Let's talk it out.
Interactive,
Mm-hmm.
do you mean verification like a client-server mode kind of thing? Like how
Yeah.
in web sessions it happens? And by non-interactive, the proof is just there and it can be verified at any point in time?
Yeah. For non-interaction, the prover just offline generates one proof, a piece of data, and then send data, either put it into email to another another verifier, or put it on chain or something. Now store in our hard disk, and it's a kind of piece of data. But for non-interaction, the prover and the verifier should be online, kind of client server,
Are there any limitations to what we can prove or we can't prove? Like the information that we want to prove should always be in text or numbers or anything? Or does it accept log formats?
Okay, so, your question was that what we can prove by using zero-knowledge proofs, right?
Yeah.
Okay. Okay, very good question. So, what do you want? Okay, here's everything provable can be proved in zero-knowledge. So basically, we can prove everything, including all the mathematical proofs. So and many things. So in computation theory, so there we can draw a picture and draw a circle to make a very clear border. That's something that we can prove. Actually, it's very, very big. For example, we can prove that a computation, piece of a computation. We can for example, that if some computation happened or conducted by someone remotely, then that guy can prove that the computation was faithfully computed with something public input. Then that guy can prove that the computation there's no just the correct result, and all the intermediate steps should be correct, and that guy can prove that. I think it's an easier way to separate something that zero-knowledge proof can prove or cannot. So if you want to prove something, that you have to you have to try to model something that you want to prove into computation. So if you can compute something, then you can prove it. Otherwise, so I don't know. So it's still a theoretical open problem. Yeah. But generally, if you can compute something, then you can prove it. For example, the validation of block, right, or transaction, because the verifying a transaction can be turned into a program, with the block as the public inputs, then the validation, the process can be proved correct. So if some miner, or validator proved, the block is valid and with some proof generated, and then other validator can trust just simply verify the proofs instead of redo the verification work. So it will save a lot of computation resources. So something that I can just keep in mind, and something that you can write a program to do that task, then you can prove it is correct. And also, for example, for the privacy is almost the same. Even the computation, conducted remotely, and probably that the program have some private input. So the private input have to. Okay. There's another. Okay, here's another problem. Okay, let's stop here. So what's your question?
No, I just want to confirm I understood correctly. So when you talk about proving, it's not like we're proving truth, like, hey, I'm here, so we're proving that. It's just proving it's limited to the computation.
Yeah, yes, it's limited to computation, yeah.
Okay.
For example, validate a signature, digital signature, yeah, it can be proved. So if I prove, okay, the weather today is not good, maybe you have to prove that this fact with some data from some official website, something, yeah. So you have to turn it into the problem into a computation problem, yeah. So, but if it can be turned into a program, then yeah, we can prove it. It's 100% we can prove it. So if we want to integrate some zero knowledge, if I want to utilize zero knowledge proofing for your application, okay, it's just like, okay, think of it this way. Okay.
Yeah, so from your talk till now that I understood about zero knowledge proof, like it's a probabilistic proof. So like the number of challenges, if we have a lot of challenges, we are reducing the probability of like someone cheating, right? So
Yeah.
And so we have so many challenges that it's very
Yeah.
impossible.
Yeah. Yes.
To
Correct.
actually cheat on that.
Yeah.
And also it's the SNARK is non-interactive. So
Yeah.
So that means it's just like one.
Yeah.
Right.
Yeah.
But what I did, and it's like hashing, so all the challenges in a hash, and so that's why it's able to do one go. But
Yeah.
what I didn't got is like let's say, for example, I want to prove like I have 100 Bitcoin without actually
Yeah.
showing
Okay.
I have 100 Bitcoin.
Yeah.
So how does the verifier have those challenges set up in a way that, what kind of challenges it knows that will 100% verify that I have 100 Bitcoin? Like, does it depend on the particular proof, what I'm trying to prove, what are the challenges? And also, how does the verifier know that challenge that I did as a prover is correct?
Okay. Okay, let me rephrase your question. So the first question is that, so how can verifier, sorry, can you say that again, your first question?
Yeah, like how does the verifier set up the challenges for a particular proof? Like
For a particular, okay. Okay, for a public coin protocol, so the verifier, the only task for a verifier is just to raise a random number. So the random number, the only requirement of that random number is it is random. Has nothing to do with the statement that the prover wants to prove, actually. So the random, okay, just keep it random as random as possible. Okay, that's all.
okay.
Yeah. So what was your second question?
So, and then how does the verifier know that the prover answered correctly or not?
Okay, so the computation, sorry, here, the verifier and the prover should agree on the statement that the prover wants to prove. So the statement. Should be kind of it's a consensus, right, between prover and the verifier. So, and also the public input, statement on the proof, including the public input. So the verifier, when the verifier checks the proof, the verifier has put the public input into the proof. So the verifier verify. Okay, the first, the argument, the first argument kind of pi, the proof. Okay, pi for proof. And also the public input, PI, public input. And then test if, okay, it's 0 for reject and a 1 for accept. So the PI actually, so, okay, PI. So the PI actually is the statement that the verifier wants to verify. For example, the pi is a signature, digital signature, then PI can be the public key, right? The signature, has a similar protocol structure with the zero-knowledge proof. So you can see, you can treat, or you can view the digital signature, the protocol kind of very similar to, but their interfaces are different. But the principles on the hood, actually, they are very similar, So here, the pi is like a digital signature, and the PI, public input, is a public key. Or other public parameters, for example, which elliptic curve that they use, and other security parameters. They both proof and verify should agree on those same set of parameters. Yeah. Okay.
How does hash function transfer multiple rows to your plan?
Okay. Here. Okay, any question from you? You use your hand. I collected enough questions, so I will decide what I will share next. Yeah, just a question. Okay, ZKP is okay. Here's ZKP, right? But here is ZK-SNARK. You know what I mean? The ZK-SNARK is a subset of ZKP. Yeah, but ZKP is a much broader concept. But here in cryptocurrency, we only focus on ZK-SNARK because it's practical and yeah, it's a very good tool to achieve something that the common the consensus protocol cannot do. It's a very good complement or. For example, if we want to a blockchain to be, lower their gas fee or improve the throughput, then I think the zero-knowledge proof will play a very important role to do that without sacrificing some, bandwidth problem, something like that. Yeah, there will be a much simpler architecture. Where can ZKP can achieve?
Yeah, because you're saying the whole ZKP is not for crypto, but the subset is good for the crypto.
Oh, okay, yeah. Okay. So I will answer you later, right? Okay. So what's your question? No question?
As we continue, I had read somewhere about this proofs and how the trusted ceremony.
Okay. Trust ceremony. What that? Okay.
You can talk about it.
Yeah. Okay. Very good.
Does ZK-SNARK have strategy against quantum computing?
Okay. Very good question. Okay. Let me first answer a question from this gentleman, and how we can use the hash to convert the multiple round interactive proof into a fancy one-round protocol. Okay, so it does like this. For example, proof verifier. So in the first round, the prover will commit something, commit something, kind of put something into a box and then locked up, and then send the box to the verifier. But at this moment, the verifier cannot open the box, so make sure that privacy is protected, the privacy from prover side. So prover sends some message. This message can be encrypted or it's just a very tiny commitment without leaking any useful or personal information from prover. And the second round, the verifier will, it's a multiple round interactive proof. The verifier will send a random number. We call it R0. So, M0, and then prover will send M1, 0, M1, and then R1, blah, 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 all the way to the MK, MK. For example, we assume that we have K plus 1 round, Then we convert it into a one-round protocol. So prover will, here we use a hash function. So imagine hash is a people. It's not a tool, it's a people. So now the prover interacted with hash function virtually. So what do you mean by virtually? So the verifier will send them 0. Then the hash function will hash the public input. Here the public input is in other words, PI is the statement that the prover wants to prove. And plus M0. Then we have the R0. And then the hash will reply to R0. Here the prover will send a second round, a second message, M1. And then the hash function will hash R0 plus M1 to get R1. This looks like the hash function will hash the history of this protocol into a new random number. And then the hash will send back R1. So blah, 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 all the way to the final message. So, but here the hash function is a deterministic function, right? So basically we put the same input into the hash function, we should get the same results, right? Hash function is a deterministic function. Then the prover can call a hash to do the interaction in home, right? Before sending the proof. So the prover can use just a call, a Python code or Rust, written in Rust, a hash function to generate R0, R1, all the way to. And that prover will record all the message in between, packet those stuff into a proof. So we got a pi, actually is M0, R0, M1, R1, blah, 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 to MK. So then the prover will send pi to verifier. And the verifier will also call the sim hash to check if the R0 is correct and R1 is correct, all the way. All the random number inside were faithfully generated by sim hash function. So the verifier will check the pi by check to replay the whole transcript to ensure that, the hash function, the jobs done by the hash function were correct. That's the principle that, now we convert the the multiple round interactive proof into a one round non-interactive proof. Okay.
Question. So during this point where there's converting the computational steps into the algebraic equations come in, where do
Yeah.
you come in at this point?
Not exactly. Okay. So you have you must have read a lot of stuff of the SNARKs, right? There are many mathematical equations, right? Especially algebra, heavily algebra stuff inside. Okay, not this part. It is called the Fisher-Shamir heuristic or transformation. So okay. Okay, and algebraic equations happen into, so what are M0, M1? So we have, okay, I will show a very minimal protocol later on to show you that, okay, how the algebra get involved. Okay.
Which part of the interaction is random?
Sorry?
哪个参数是随机的？
Okay, it's like not the real randomness. It's okay. There's a jargon from the cryptography community that's called the random oracle model. ROM. ROM is called ROM because we believe that we believe that the hash can be used as a oracle, a honest, powerful, mighty oracle. We always generate unpredictable random numbers. But it turns out, if the hash function, because so far we have no ideas that how can the prover can attack this random oracle model, O for oracle model. So it's typically 13 years ago, some cryptographers didn't accept those kind of assumptions because it looks weird. But right now, everyone just happy with that. So okay, the random oracle model. Okay, the hash function will kind of. So here we some hash function cannot be used. I have to say. So we have to use, for example, the switch to 56 or SH3, for example, the cake, right?
So it means that we give a message 0 to hash function, and the result 0 is regarded as a random one.
Yeah. So I have to explain something. Why the prover cannot predict the R0, right? Basically, it can, right? Basically, prover can get R0, but only after M0. So if the prover wants to take advantage of knowing R0, if a prover, okay, at the second round, okay, here, the prover, okay, prover knows R0 now, so prover wants to attack. The prover has to modify M0. But if prover modify M0, the R0 will be different. So that's the way we're using the hash function to prevent prover from taking advantage of knowing R0. Okay, I stop here for 2 minutes. So this way is very smart. It's a smart qubit. It's called a very famous technique called field Shamir transformation. So then the prover can generate that in the interactions without the verifier, right? Then the prover can generate the proof in home, And then after generating the whole conversation or the whole transcript and pack them into a piece of data, and then this piece of data can be, okay, we call it zero proofs. ZKP here, this as ZKP, okay. I have to say, okay, it's a one of constructions, approaches of construction. It's not the only one, okay. But this one is the most popular today. Many, 95% of the proofs built this way, but not all. Some traditional try to set up with the Gross 16. Okay, it's not built like this way. Gross 16 is totally different.
They all based on the same ideas.
Not that same. Okay. Yeah. There's many ideas today in the zero proof sector. So many new ideas. Yeah.
So another question. So this interaction between the prover and the generator, right? So the prover sends a message, and a number. What determines how many times we have this interaction until we get to MK?
Time. What do you mean? But
how many? Yeah. What determines how many times we're going to have the?
Okay.
Until we get to MK?
How many rounds or the cost?
Yeah.
Cost.
What determines how many rounds you're going to have? When the
How many rounds?
yeah.
Okay. It depends. There are many different Ziggy SNARK protocols, and some protocols can, for example, Gross 16, only one round. For STARK, it's a log n round. Here n is the size of the problem, so I have to say. And for example, Planck. Have you heard of Planck? Planck is kind of O1, so O log n. It's constant number of rounds between prover and verifier. But Planck also uses the Feld-Shamir transformation. But the rounds is kind of a constant, maybe 6, 7, or 8, or 6, 7, 8, something like there are different variants of different Planck. Planck is a family. There's many different versions. Yeah. But for STARK, we have logarithmic of a problem size. But still, it's quite low, quite low. Imagine that, okay, if the round is too many rounds, that the proof size will be bigger, right? Yeah. Okay, everything okay? I hope everyone can follow. Even I haven't started this topic, but it's okay. I'll be very happy if you know something, more than before. I'll be very happy. So I would like to answer any question. So some question from this lady and about the quantum computing threats. I will talk it later. So after draw a picture for you that how modern the SNARK system looks like, there's many it's kind of a complicated system right now. So, okay, any more questions? Okay.
Yeah, when you get to how it's post-quantum secure, could you also maybe talk about the stacks? Because normally say the stacks are post-quantum secure, so could you maybe differentiate between the stacks in terms of what makes it post-quantum?
Okay. First of all, it's my pet peeves. And SNARK also a SNARK. SNARK is a family of, okay. Some people saying that, okay, the ECC-based, ECC elliptic curve, ECC-based SNARK, they call it SNARK. And SNARK actually is linear code, not linear code, IS code based SNARK for some historical reason, and the author of SNARK, they create a new family called SNARK. SNARK is kind of a RS code based. RS code is a Reed-Solomon code from the coding theory. As the security cryptography assumption to okay, this one is a post-quantum secure post-quantum how to say it, resistant post-quantum quantum computing resistant. And the ECC okay, it depends. Because there's different approaches to build a cryptographic assumption over elliptic curves, but most popular one is not quantum computing resistant. So basically, that the security assumption relies on the hard problem of factorization of a big integer. So that one we have a known quantum computing algorithm to solve that problem in practical time. So, but there's many other different approaches. So it depends.
I have a question more about, though we are not yet there, but it's more about quantum computing. So
Okay.
how are protocols kind of preparing themselves when quantum will be added?
How protocol what to prove?
Because it poses more of a threat.
Yeah.
More about how the cryptographic and all that stuff works. So like, how are most chains of protocol preparing themselves against this?
Okay, I don't know. But currently, Ethereum, they have put a lot of efforts on trying to, do a lot of research about the post-quantum SNARKs, post-quantum signature schemes. But the problem is much more complicated than we imagine, I think. For sure that elliptic curves, some assumption over elliptic curves will not be safe, we know. But there's still some other voices saying that, okay, there's a sure algorithm will have some serious problem if the problem is big enough that this algorithm probably, won't work as we expected. We expect, for example. But I'm not an expert on quantum computing and something. So I just someone told me in last month, but I'm not sure. So it's still unknown places, and even some post-quantum approaches. They claim they post-quantum, but it's just based on the ignorance, right? Because currently we don't know how can we attack it. It does not ensure that in the future, nobody can somehow a genius invent something new, to break the assumption. Yeah. But I have no idea about that. Just okay.
I have a problem. It's not all ideas of ZTP are based on the hash function trace multiple round to run on.
Sorry, you have.
就是不是所有的 ZTP 都是基于这个。
Yeah. Yes. But for example, the Groove 16 is based on linear PCP. It's a PCP approaches. Okay. No questions so far. Very good. So that's here. Yeah. Okay. Today we're going to share some, okay. First of all, we'll draw a picture for you. It's like a ZK SNARK. Okay. I forgot something. There's a ARC, right? ARC. So AR means argument. Then the K means proof of knowledge. And the S means succinctness. So argument, argument is a cryptographic jargon. Basically saying implies that the proof size can be very, very small. Yeah. But so argument implies that, okay, if the prover has unlimited computation resources, so imagine that the prover has a future, quantum computer, for example. The prover can break the protocol. The prover can cheat. So the argument means that we assume the prover, the computation resources from prover is limited. So that's an assumption. But okay, that's the cost. What did we benefit from that cost is that the proof size can be very small. The smaller the proof, the easier the prover can cheat, right? The prover kind of is like the prover provides more evidence to convince the verifier. The less the prover provide, then easier to cheat, right? This is okay. So argument allows us to build a very small proof, but we just assume the prover is not so powerful. Yeah. But it's okay. In practical, it's okay. The K is proof of knowledge. Okay, it's subtle. It's also a proof of knowledge means that the zero knowledge proof the statement is a proof of something exists, but the verifier cannot see. It's tightly related to privacy protection. So there's another name, SNARK, and SNARK. But SNARK, in additional, the prover proves that some private data the prover has or owns some private data, but the prover don't want to show to the verifier. But the prover prove, okay, I own the data. It's not data stored from other people, It's I own it. For example, the digital signature, it's kind of a proof of knowledge. The digital signature proves something, prove that for example, Alice owns the private key, right? it's exact the Alice signed the signature, not the other one else, right? And, okay, I stop here for 1 minute. So 1 minute. So proof of knowledge is yeah, you can ask AI for more information. And succinctness is like the proof, the size of proof should shorter than the problem itself. The proof should be small, and very small. Imagine that, okay, if we valid like in Ethereum, on Ethereum, if a validator want to verify a block, right? Actually, the verification work can be large, right? There's many transactions there, so for each transaction, we have to every state transition is correct, and every signature is valid. So there's a lot of computation inside. But succinctness will, allows us to build a proof much more smaller than the size of computation. So that's why I said, okay, the ZK-SNARK is very suited for the cryptocurrency because S allows us to build very small proofs. So such that we can pay a little gas to put the proof on chain, right? Because the proof is very short. So otherwise, the proof can be, megabytes long, or be too large to put it on chain. So, okay, it's a ZK-SNARK. Okay. There's many, as I mentioned before. So ZK-SNARK, there's many different approaches to construct the ZK-SNARK system. But I will show you a very popular architecture. Okay. Here, we have 4 layers. The ground layer is for math. So algebraic equations, so the many math here. Okay. Here is something called polynomial commitments. It's a protocol. Okay, it's a protocols. Okay.
Isn't it the same as commitment openings?
Sorry?
Commitment openings.
Commitments opening?
Yeah.
What does that mean?
When the commitment opens, now the verifier has to now accept or reject.
Yes. Polynomial commitments is some commitments protocol that yes, the prover will commit to a polynomial instead of a piece of data. The data is actually the polynomial over finite fields, something. And then later on, the prover can open. It depends on how you design the protocols. So, okay. The second layer, bottom up, is the polynomial commitments. And then here is like a polynomial IOP. Okay, let me. Interactive. Oracle protocol. Okay. Here is the arithmetization. What does that mean? It's support general commutation. Okay, so now we have two main approaches to how we can model in general computation. So the first one is like a circuit. So you may have seen some, the terminology have occurred in many technical articles, right? Circuit and a ZKVM. It's like, actually we call it RAM. It's a machine like, it's okay, let me put it here because ZKVM is it's like, because the VM can, we can turn any terminated computation into a trace, execution trace of some VM, right? So basically, we can use either a VM traces, to represent some computation, or we can use a circuit. Circuit, we have Boolean circuit or arithmetic circuit. Okay, imagine that now you are trying to use the proof to do something in your application. So first of all, you have to identify the computation that you want to prove. Now you have to turn your computation into either a circuit or a ZKVM or a VM, trace of VM. And then you have to choose which protocol IOP that you want to use. For example, the SNARK or Planck or many others, GKR protocol like. And then you have to choose which polynomial commitments that you use. Different polynomial commitments, they have different proof size, whether it is post-quantum, the proof, whether the proof size is kilobytes long or megabytes long or even much more smaller, probably. And then math, okay, always we treat this part as a black box. We just use it, but this part is kind of very interesting. But well, okay, it's a architecture of a modern, but not all. I have to say, not all ZKP or ZK-SNARK follow this paradigm, but this is the most popular one. Okay, any question here? Okay.
So in that architecture, right, when we take it back to the Cairo virtual machine, because it falls under the ZKVM, so I have a question around that. So the way it works is we have the Cairo algorithm, right?
So sorry, Cairo?
Cairo, yeah, because they use the stacks in the...
Cairo? You mean?
In the stacknet.
SNARK, yeah, Cairo, you mean the language? Okay. Okay.
So we have the Cairo virtual machine.
Yes.
So when I see this architecture, I wanted to ask, there's something we normally learn whereby you have the Cairo algorithm, it is fed into the Cairo virtual machine, creates the execution trace.
Yeah.
And then when we now talk about the AIs, the algebraic intermediate.
Okay. Yes. Here, arithmetization protocol will actually, okay. Yes. That's something in between. Yeah. 1.5 air. Yeah. It's like, you can see air as a circuit or it can be seen as a VM traces. But actually, air is more close to VM traces. Yeah, very good. Thank you. So air is a
I have a question. Where is the method stereo in that architecture?
Here we have virtually a proof verifier, and here we have virtually a proof verifier. Because these are just algebraic options, or we build some functions or something. Well, here are some protocols. Maybe a lot of protocols. A big protocol, framework protocol with some many sub protocols inside to form form this layer. on this layer. And here is also I would say more lightweight than this layer, but more math here, yeah. Because polynomial community will rely on some algebraic structures here. So this one a little bit more difficult to understand, but the protocol is kind of much more smaller. But this one kind of a Lego game. Basically, we have a lot of different, for some function, we have a lot of candidates protocols, and we can choose something and build them, build your own protocol, for example. So they're actually, this part is kind of a Lego game. Okay, this part is we have some choices. We have to choose some polynomial commitments according to your application. Yeah.
So if I have a program about the weather, so
Weather? Oh, okay.
What is M0 as maybe?
Okay, weather. Okay, you have to. First of all, you have to clarify or build your computation. You have to, for example, the weather. You get some weather data from official website. Then you do some calculation. So you have to write a piece of code, either in circuit or in VM. For example, written in Rust, and compile the Rust into VM traces. And then you invoke some like a Planck, for example. In Planck, the M0 will be like okay. In Planck, the M0 is like a prover will send some commitments. Yeah, it's kind of yeah. So what time is it? Yeah, still have time. So yeah, I can show you a minimal protocol. Yeah. So far, so any more questions?
So this is like the whole architecture for like the ZK SNARK, right?
Yeah, ZK SNARK. Yeah, ZK SNARK.
Is that stages of what's going on there? Because at the base you need math, but then the third stage you're saying it's like Lego. So what's happening in that diagram?
Background. I mean
The diagram.
diagram.
Yeah, the one that you've drawn. Like now you say they use math, then at
Polynomial commitment.
interactive protocol, you say it's like Lego. So what do you mean by that?
Okay, so the Lego. Okay, I mean, so for example, the prover and verifier. Okay, polynomial commitments, first of all, is a small protocol. For example, so the prover and verifier, the prover has a polynomial fx as the private data, and the prover you ask that I want to from for example from finite field P, and the verifier wants to know what's FA. So right, and then prover can prove to verifier that the FA equals to some V. So sorry, I don't know use V as W, and then the prover verifier can interact with the prover, right? The prover can prove that FA equals to W. Okay, it's a it can be used as a sub protocol inside a much bigger proofs. So we build it like a module or Lego block, And then we can put it here, prove FA equals to W and FB equals to X. Not X, double prime. So where I use the double line arrow, so it means that, okay, here is a subprotocol invoked, okay, just like this way. Right? But here we're working on a much more abstract protocol. We call this subprotocol just as a function call. And then, okay, here is a, like still can, for example, this way can prove, for example, a membership proof. We prove that prover proves some A belongs to a large set, right? And still in a much larger proof framework. So prover can prove X belongs to S and another Y belongs to S to call this subprotocol as a function. So it's what I mean by Lego game. But here, actually, we have different style, different approaches to achieve that polynomial evaluation proof. Then basically, we can replace this one to another. Let's kind of, we have different libraries. They have same interface. And then we just use something that we want to replace this protocol with another because the new protocol has better performance or better additional function that we care about. It's what I call a Lego game because we can basically combine different subprotocols together to make a bigger protocol. It's like programming. It's basically like a programming, but programming is programming about the protocols instead of function call. The function call is you compute something, right? The prover. The protocol is in each module, the prover will prove something. But we want to prove a bigger statement. We'll rely on some sub-goal or some for example, the membership proof. The membership relies on the polynomial evaluation proof. Then we can build a much larger. So basically, the modern SNARK system, if I take a closer look at this layer, we will see a lot of proofs, a lot of protocols. They are integrated into one protocol. But that's very tricky because sometimes we cannot find the clear border between this invocation because sometimes for some performance consideration, this protocol, the sub-protocol and the framework protocol, they combined, or sorry, they mixed together to make sure the better performance sometimes. So now that, when you take a look at the code, you cannot get that picture because all the sub-protocol and the protocol, they mix together just for the optimization. But if you read more about the protocol design, you can feel that. You can draw a line to separate the subprotocol from the framework protocol. Okay. Okay, is that you want to ask? Okay.
So what I also know about ZK SNARKs, that we have I don't know if I'm going ahead, but we have like the Sumcheck plus for the commitments, and then we have the fiat sharing. So how do you connect this to the structure?
Commit what?
Connect this to the structure.
Connect what to the structure?
So like for the ZK SNARKs, we have like the Sumchecks.
Yeah. Okay. 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 For this one, okay. Sumcheck happens here as a core protocol, and also here. So we will use the Sumcheck as a very primitive protocol, sub-protocol, sub-sub-protocol, and build, and we'll gradually improve more powerful and more powerful mathematic equation or statement. And then get bigger and bigger and bigger, then we can prove all the general commutation. Yeah. So you know your head. So any question?
So like when we are generating the random things, right? So
Mhm.
it have to be in a trusted setup to generate that random things that we are generating.
Mm-hmm.
So how do we make sure it's a trusted setup? And also like after we are done with the ceremony, how do we make sure that those secret values are disposed?
Okay. Okay. There are many. There are different approaches. For example, the Gross 16, and also the Pinocchio. I don't know how to spell it right. Pinocchio, right? Pinocchio. Gross 16. They require trusted setup. But the question is, I have to take in deep into Gross 16 to understand why we can conduct a multiple party cross setup to make sure that nobody can leak or can know that secret. So that's the very big topic. So I cannot, sorry, cannot explain it today. But okay, this is the first one that probably you see, because there are many articles about trust setup. Probably a lot of people afraid of this one, saying, okay, trust setup is not good. But as far as I can see, trusted setup is a way to do some extreme optimization, because we have, for example, for Gross 16, actually we put a lot of pre-processed statement inside the trust setup. So that's the reason why the Gross 16 can generate the smallest proof size so far. So we can say that optimization. So for you, but some people will, complain that okay, trust setup is too heavyweight, and then we can use the KZG10. It's a polynomial commitment instead of the SNARK. So we can have a universal trust setup. But the universal trust setup, even the trust setup is still too heavyweight, but the setup result can be reduced for many times. For example, you want to use the KZG10 to build a SNARK in your application, you can just reuse some guy. They already had the universal trust setup. They put all the data on the GitHub. Then you just download blindly those data. But if you don't trust, you can do, because you can do more around above this universal trust setup, unless just you do round to append to the result. Until some moment that okay, can be trusted, that okay, you can use the trust setup. But here the Gross 16 trust setup is circuit specific. That means if you change your computation, that you have to redo the trust setup. It's too heavy. So that's the reason why less and less people use the Gross 16, because too heavy to use. But KZG10 is much more practical, and there's another ECC-based, for example, the bulletproof. We have the transparent setup, transparent setup. Okay, still we have some toxic waste inside, but the security assumption is that the hash function used inside the transparent setup is good. It's it's not compromised, so that we can trust the result. We can use that to build a secure application. But I can say, okay, just it's a something problem on the surface. It's not actual we don't have to use the trust setup. We can choose many other approaches. So yeah, I think you can go deeper and trying to identify why it works and what's the potential security vulnerabilities of these approaches. I have to say you have to be careful because it's so easy to introduce vulnerabilities. Yeah. Any other question?
Aside the KZG style, you have the IPA style, right?
This one?
Yeah.
Yeah, sure. IPA, yeah. Yeah, it's inner product argument. But I don't like this name because IPR, there are many inner product arguments. The white people call it IPA just because, yeah. Yeah. I don't know. But okay, sometimes I call it bulletproof hyphen the IPA. Because there is a KZG hyphen IPA also, so I have to distinguish them. Any questions? So I'm sorry for I haven't started the topic today. I hope you guys know something, and get some intuition, basic intuition or understanding of how the design proof works. Yeah.
Can you give us an example of like how to enroll can't always like going down?
Yeah, this was I wanted to. Yeah, this what I wanted to share. Yeah. Okay, I think we have already 1.5 long. So if you are interested, you can stay here for, I will draw some more pictures. Take a deeper look into this model structure, and but I have to the stuff will be dense.
Yeah, I think our next workshop is 4:45, so we have a lot of time. We have a lot of time here.
Oh, okay, really? Okay. So okay. Okay, yeah.
Just a suggestion, like use kind of analogy examples so that we get to understand it in a different manner.
Sorry?
I'm trying to say like you kind of do some examples like real world use case so that we get to like digest it more better.
Okay. So more examples. So there are two categories of examples. First of all is like imagine we build something application also for some application where we show that how you can build the application by using these SNARKs, or we show some a small example about how SNARKs works. So yeah. So but what I prepared is like these examples pretty inside the SNARK framework. For application, I think, yeah, I can share something, but okay. I think, okay, this part is more math. but I guarantee that you can understand, only high school math required. And the application parts can be more practical. Yeah, I can show some example that our team did before. So which one? Take into the SNARK modern system, or some application example. So any idea? So you don't want to know. Basically, you don't want to know how Sumcheck works.
We are
Example first. Both.
So basically, I want you ask more questions, so I can know that which part probably more useful to you. Yeah. Okay, let's stop here for 5 minutes. Okay, a question. Then I think this part is more math, but not so much. Yes, so it depends on that how much math that you can tolerate or something.
I have a
Okay.
question.
Okay, yeah, good.
Why we need two layers of P and V? It is
It's a support protocol. You can see that. Okay, this layer will be sub protocols invoke many times on this layer by a framework protocol. So just like this, this module will call this module. This module will call this module. Each module will have different proof and verifier because they basically prove different theorems, right?
so every ZKP need two layers of
Sorry?
每个 ZKP 都需要一个偏数学的，一个偏工程的那个一个。
Okay, your question was if every ZK protocol has two aspects, one from engineering and one from theoretical math, something.
Just these two layers.
Yes, I think so. Yeah, basically there will be many algebraic equations inside. And also there are many practical engineering problems inside. So, yeah.
So the second layer is
Second layer here, this.
up
Okay.
for engineering.
Actually, it does not, because we have to prove the protocol is sound. So there are many cryptographers working on this part. Yeah, pretty. It's not that easy. It's not that easy. Yeah.
What is the main difference between two layers, the second one and third?
Okay, this one. Okay, polynomial commitments. Okay, here, polynomial interactive oracle. So oracle, what does oracle mean? Oracle, like we just unconditionally believe oracle is honest, and oracle never cheat me, either for prover or for verifier. So the prover, verifier, and oracle. Here, oracle. So oracle will have a conversation between prover and the verifier, and then the prover verifier unconditionally trust oracle. It's like a centralized entity, right?
It is centralized.
Yeah, it's a centralized, right?
Okay.
Because prover verifier never, question Oracle. So, but Oracle can be, with Oracle, this centralized entity, then the protocol design will be much, much more easier. Because we have something we can trust. The third party, okay, we can trust it. We ask them many questions. I believe that all the replies or answers will be correct. So that's too good, So it might be easier to design protocols here. But here, we will replace this Oracle with another protocol to make sure, okay, this centralized entity at this layer can be also decentralized by using some math, Yeah. So something like the polynomial commitments realized the Oracle. Yeah. So when you say some academic papers, I think most of them working on this part, and I will give you some options. Okay, which polynomial commitments can fit into this protocol, and I will show you a table, which polynomial commitment that you use and what results you can get. So different polynomial commitments will have different features. For example, the famous STARK versus SNARK basically means the KZG10 versus, the story STARK versus SNARK actually is Fry. The Fry is a polynomial commitment protocol versus KZG10. That is a true story. Yeah, but this one is too technical, and but SNARK STARK kind of.
It's engineering.
It's not engineering. It's all the features of STARK and SNARK based on which polynomial commitment they choose. So, yeah.
So STARK and SNARK is there too.
Yes, here STARK SNARK, and here is the polynomial commitment. Actually, they compare Fry with KZG10, but with different names. Yeah, that's the reason. Yeah.
So Fry is layer third.
Oh, yeah.
Oh, okay.
With Fry here, for example, we have bulletproof IPA, Fry, and KZ10, and many others. Yeah.
So I have another question.
Okay.
So the hash function is a piece of polynomial commitment.
No. Hash function is a hash function. Hash function, we use hash function for different purposes. Yeah. But here, if you use Fry, we'll use hash function to realize the Merkle tree. They will commit a vector. We're using a Merkle tree, then using some hash function. Yeah. But yeah, hash function is everywhere. Yeah.
So in the basic idea, we use hash function transform multiple runs to one run.
Yeah.
So in that architecture,
Okay.
there is a hash function compared with.
Okay, here and here. Yeah, basically we
I get it.
we compile this into the one round non-interactive protocol. Yeah. Here we use Shamir transformation into pi.
We call this progress as hash function.
Progress.
The progress of two layers. 就是我们把这两层的那个处理叫做 hash function。
We call it a Feder-Shamir transformation. By using a hash function.
I mean that this architecture meant run multiple runs to one run. And our basic idea is also use hash function to transfer multiple runs to one run. So where is the hash function in that architecture?
Hash function?
Yeah,
Okay, we can put it here. Or put it here. Yeah, put it here, hash function. So because there is an option that if we really want, convert it into a non-interactive protocol, but we don't have to for some application. Maybe we just insist on interactive for some application. That in that case, we just don't use the hash function. But most cases we use the hash function because it's too good. Yeah. Okay.
So when we had previously asked about the things that make, for example, the SNARK post-quantum secure, it's the fry, right?
Yeah.
That makes it different from the K.
Yeah. Yes. Actually, we are talking about the fry. Yeah. Yes.
就是我们的那个架构是让多轮变成单轮，然后这个也是多轮变成单轮，然后但它用了 hash function， 这个是就是我们的这个架构，大家怎么等价？我是这个。
Okay, here we just convert to. Okay, you can say we convert the whole framework into a because. Yeah, here, okay, we just convert 2 layers into non-interactive. Or we can say that, okay, every layer will have a hash function. We always turn into a one round. For example, we have multiple rounds. Convert it into one round protocol at each layer. That's great. Basically, no difference. Yeah.
So hash function is a part of polynomial computing.
Sorry?
The hash function is a part of.
Yeah, I can say that. You can say that. Yeah. No problem. Okay, do you guys want to have a break? Yeah, okay. And then if you are interested in some questions or something that I prepared, then you can stay. Yeah. Can I? Yeah, I should take a picture. Sorry. Yeah, thank you. Okay, yeah, thank you for your questions and thank you for your attention. Yeah, thank you.
You're saying we have not begun the workshop?
I think it's just a break.
Thank you.
Yeah.